Hello again, and here we are, the second of the kitchen series on gravitational waves. I've taken over a pretty girl's kitchen, and we're doing relativity. Now, in the last lecture, we've seen how space and time got joined together in special relativity, and how we got to measure time in meters and space in seconds, if you want. And then the speed of light is 1, as in 1 meter of time and 1 meter of space. And now in general relativity, Einstein allowed space-time to vibrate. Space-time comes to life as a dynamic entity which changes shape, and changes form, and supports waves. We call them gravitational waves. Now, the matter content is what dictates, like as John Wheeler put it, space tells matter how to move, and matter tells space how to curve. And that is formalized through the Einstein equations, where G is the Einstein tensor, and comes from the curvature of space-time, and T is the stress-energy tensor, which describes the matter content. Now, as G is a form of curvature, all forms of flat spaces will have G equals to 0. And only curved space will have some sort of non-zero G. Now, the solutions to the Einstein equations will be, first of all, the first solution to ever be proposed was a gravitational wave, a plane wave. And then the next thing that came was the Schwarzschild black hole. Black holes from which not even light can escape. Now, a black hole has, in its very definition, you have the horizon of a black hole, which is where time stops as seen from infinity. And once you go inside the black hole, the radial direction becomes time-like. Which means that once you cross the horizon, you are bound to go forward in time, which means towards the center of the hole. These are all time-like world lines. So the reason why you can't go out of a black hole is that it requires going back in time. Now, will you say black holes are black and they emit nothing? Which is where their name comes from. And yet, black holes are the most luminous things in the universe. There are several ways for black holes to be luminous. One of them is quasars, or quasi-stellar objects. Maybe you remember that poem, "Twinkle, twinkle, quasi-star, we all wonder what you are, brighter than a billion suns," and so on. So quasar is a black hole with an accretion disk. By the way, given how small black holes are, of all things in the world, if you want to hit an object, among objects of the same mass, the black hole would be the hardest thing to hit. So, if we were to make a black hole out of the Earth, we'd have to squeeze the planet into this. And by the time you squeeze the planet into this, you'd have all the mass of the Earth in this. And the gravitational field where we are would stay exactly the same. Now, imagine you have an asteroid, a meteorite or a comet or something, come and try to hit the Earth. Right now, with the Earth being so big, all it has to do is come within 6,000 kilometers of the center of the Earth, and then it succeeded and it hit the Earth. But if the Earth was this small, it would be extremely hard for that meteorite to hit the planet, or the black hole, because now it's a black hole. So then what it would do instead is that if it comes within a few thousand kilometers of this, which would have been a clear hit today, it will keep rotating around it. And if it gets captured, it ends up being a satellite of the black hole, moving in an ever smaller object. Now, as it gets closer to the hole, the centrifugal force has to be equal to the gravitational force, the gravitational pull of the black hole, which becomes very, very big as you get very close to the black hole. And when you come close to the horizon, when you touch the horizon, you end up moving at the speed of light. So it's going to be hard. Well, actually, I'm wrong. You end up moving at the speed of light when you're about 3m away from the center, I think. So, and once you pass that 3m point, which is the innermost stable circular object or orbit, you have no stable circular orbit left, which means you're bound to go in the hole once you cut them too close. But then what you have is that this thing that has to form the black hole form an accretion disk around the hole. And as they get closer and closer, the accretion disk becomes superheated. And that very hot accretion disk then starts to emit light. And this is how a quasar works. So a quasar is a black hole with an accretion disk around it. And this accretion disk spins very, very fast and emits light. Now, that light that comes from the quasar is a bit surreal because its spectral lines, if you look at the star, the spectral lines of a star are rather sharp. So you have the Lyman alpha line for hydrogen, and then you have a few others and so on. If you're looking at the spectral lines of a star, they're quite sharp. And if you look at the spectral line of a black hole, of a quasar, they're quite broad. So this would be your Lyman alpha, which would be shifted to somewhere else. It would be a longer wavelength because time is being slowed down. So it goes here, but then instead of being a line, it becomes quite a broad thing. And it's a broad thing because this light is coming, first of all, it gets shifted because it comes from a place where time is slower. But then the line gets broad because different sources at different points inside the accretion disk will have time run at different speeds. And the difference in the speed of time across the accretion disk gives you the broad nature of the Lyman alpha line and of all the other spectral lines. So first of all, it is a little bit, it's broad, it's shifted, and then you also see them double. When you see them double, you could see them double because of the light coming to you and light coming away from you in the accretion disk. So actually, your line will be one here, and then one slightly farther away. So this is what would have been one spectral line in a normal star, quite sharp and narrow, and becomes something like this in a quasar. And quasars, in terms of energy output, one quasar ends up can easily be as bright as a whole galaxy. So looking at a single source, one black hole would shine away surreal light into the universe and as much light as a whole galaxy. Now, where does this light come from? Where does the energy come from? Because you're looking at as a matter burning machine, a black hole ends up being a lot more efficient than a star. If you're looking at the fraction of the matter that gets emitted away as radiation in a star versus a quasar, the quasar will emit a much larger fraction of the matter it burns than a spartan. And where this comes from is the gravitational potential energy. So the energy of the material running away in the accretion disk comes from going down the gravitational potential well of the quasar, of the black hole. And then eventually the matter goes inside the hole, and then not even light can escape. And the hole itself is black, but the region around it doesn't have to be. So there's one way for black holes to be bright, and another way for black holes to be bright is when they collide. So when two black holes collide, they will shake space-time around them. If you're looking at this black hole, it slows down time next to it. This one slows down time next to itself. As they spin around, the slowing down the spin time of the time ends up having a periodic nature for, say, a clock measuring time here. So then this is what we call a gravitational wave. Big heavy objects that dance around and shake the space-time around them. And if you're looking at the amount of energy that gets emitted as gravitational waves and black holes collide, again, it ends up a significant fraction of the mass of the binary. So a significant fraction of the mass of these two objects end up emitting in the form of gravitational waves, and that happens in a few amps of time. Now we measure time in general relativity. We measure it in units that are linked to the mass of the object. So for the mass, for the sun, the mass of the sun would be, the Schwarzschild radius of the sun would be 3 kilometers. So the mass of the sun would be 3 kilometers. And if two solar mass black holes collide, you'd have a fair fraction of the mass of the binary be emitted in the form of gravitational waves in a few kilometers of time. Now, a kilometer of time, if you want to think of it in seconds, would be a kilometer divided by the speed of light in seconds, which would be a pretty short time. And in that very short time, when black holes collide, they can emit away a significant fraction of the mass of the binary, which makes a black hole collision, like a single event, for that short period when it's very bright, it makes it more luminous than all the stars in the universe combined, quasars included. And that's one event only. And it's this event that we've seen with LIGO. Now, the problem